All right, this video is designed to show some of the math steps involved in the Clausius, Clapeyron, and Arrhenius equations. They are both basically the same equation, just using different variables. And it involves a natural log and some inverse temperatures and a lot of algebra. So the first thing you have to be aware is making sure you have correct units. So in both cases, the temperatures must be in Kelvin. So if it's given to you in Celsius, make sure you convert to Kelvin. R is 8.3143. Or 8.314. There is another version of R that is 0.0821, and that is not the version that you use for these equations. For the Clausius-Clapeyron, you have pressures, and for the Arrhenius, you have rate constants. So then the last tip is making sure that when you plug in for pressure 1, that you put temperature 1 in the correct location. And when you plug in for pressure 2, you put temperature 2 in the correct location, because these are paired values. This pressure goes with this temperature, and this pressure goes with this temperature. And there are multiple versions of these equations that rearrange the temperatures and pressures and negative signs. So make sure you pick one equation and you use it consistently. All right, so we're mainly going to focus on solving for this spot or this variable, the same variable in both equations, and solving for a pressure or a rate constant, which is inside the natural log. So you have to know how to handle the natural logs. You could also solve for a temperature, but that's not as common, so we will not be going over that. So our first example is involving the Arrhenius equation. The problem is given here. I'm focusing more on the math and not plugging in, but you can pause the video and make sure that you get these values. I was given Celsius, so I made sure to convert these temperatures to Kelvin. All right, so just looking at the math, I can do this division and then take the natural log of whatever that number is. So natural log of 12.9629. When possible, carry all the digits in your calculator. And then on the other side of the equation, I'm going to rewrite that temperature part as 600 inverse minus 650 inverse, because that's all 1 divided by a number is. It's that number inverted. So that you can see that that ends up being in the numerator. All right, so we're going to end up with E sub A times 1.282 times 10 to the negative 4 over 8.314. And then if I take the natural log of this number, and there are 2 buttons on your calculator, a natural log and an LOG, and on some calculators, they're on the same button, and you have to press the button twice or to scroll through the different options. So the natural log is 2.562. Again, I would try to carry more digits in my calculator. All right, so now I'm just rearranging to solve for this variable. So I will multiply both sides by 8.314 and divide both sides by 1.282 times 10 to the negative 4. And so if I do that math, I end up with the E sub A equal to 166,156. And this is in joules, because 8.314 is joules per mole Kelvin. So when I solve this, my energy unit is in joules. And a lot of times you'll be asked to convert to kilojoules, which is dividing by 1,000 joules per kilojoule. And that will equal 166 kilojoules. All right. In the next example, I'm going to use the Clausius Clapeyron. Again, read through the question, make sure you know how to plug in. The temperatures have been converted to Kelvin, and the delta H has been given in kilojoules. So I need to plug in joules because my R, 8.314, is in joules. So that's also a common mistake that happens. And my temperatures can be any, or my pressures can be any unit as long as it's the same one. So now I'm going to solve for a variable that's inside the natural log, and sometimes that's tricky. So over here on this side, it's all numbers and math that we can type in, but maybe to make it a little bit easier, we can rewrite it again as 338 inverse minus 298 inverse, so it's clear where these numbers go. All right, so on that side of the equation, the first thing I'll do is the inverse so that we can break it down. The inverse temperatures subtracted from each other are negative 0.000397125. Again, carry digits in your calculator if all possible. All right, and that's still equal to the natural log of 39 over P2. So when I multiply the 32,000 times the negative number over 8.314, I get negative 1.53137. And that's equal to this side of the equation. So I'm going to rewrite that over here so you can follow all the steps. Natural log of 39 over P2, it's inside parentheses, is equal to negative 1.53137. So make sure you don't lose your negative sign. All right. So anytime you have algebra and you have something that's inside a parenthesis, you usually have to figure out how to get it out of the parentheses. So I have to deal with this natural log first. So natural log goes with the E on your calculator. There's lots of E's on your calculator. Usually it's the E that is in tandem with the natural log. It's not the scientific notation E. And you also have an LOG, and it goes with this. So these are the inverses for each function. So for natural log, you do E to both sides. So that will get rid of the natural log and leave you with 39 over P2. But then this calculation you have to enter on your calculator. So E to the negative 1.53137 is 0.216239. All right, and now you can cross multiply. So the next step is often tricky for students because the variable is in the denominator. So always cross multiply. So I'm going to get 39 equals 0.216239 times P2. And then divide both sides by this number in order to isolate that pressure. So 39 divided by that number gives 180.36, and that is equal to P2. So that covers some of the different math using these equations and natural logs.